This is the Maths 2012, just going to do the first 10 multiple choice questions. We've gone so far back in time now that the cover page has changed, which is exciting stuff. I'm still aiming to get back to 2009, which is the paper that I took, so I've got a few more of these to do. I think it's going to be a bit of a speed run because this paper was very pleasant and very nice. This is a circle, radius 2, so let's draw it, of course. Now you could do lots of fancy algebra here, or you could just draw each and every one of these. This has y-intercept of 2 and gradient minus 1, but a 2 is here, gradient minus 1 takes you down there, so that's clearly not a tangent. This here could be, because it's got a y-intercept down here somewhere, and the right sort of gradient. Let's leave it for now. This one here is a vertical line at root 2, clearly not a tangent. And this one here has a y-intercept of root 2 as well, negative gradient, clearly not a tangent either. And so we're down to this one, which looked good just when we were sketching on our heads, and is in fact the correct answer. Good, number B. So let's deal with this, make that 4 squared, make that 2 squared, make that 2 cubed, and then we can multiply out the indices, then we can add them all up. And for this thing to be square, we need this number to be even. Because, of course, when you square root, that's the same as raising to the power of a half. So if you've got something like 2 to the 14, you can raise that to the power of half and get an integer 2 to the power of 7, because you just halve the 14. But if it's an odd number, then you can't do that. You'd halve it for a decimal, and then 2 to the power of 2.5 isn't an integer, is it? So it's not a square number. So we just need this to be even. And okay, so does that happen when k is even? Well, clearly not, because if k was even, you could still make this odd, and then you'd have even plus odd, so that clearly doesn't work. What about k plus n is odd? Well, let's just try something. Let's just try k is 1 and n is 2. That makes these two add up to 3. It doesn't give me any restriction on m, so I'll just make it 0. But of course, now we have 1 plus 3 lots of 2 is 7, and that's not even. So that doesn't work. This is also a counterexample to this, because 0 plus 2 is even, and this is odd, so that doesn't work, so this must be the correct answer, which you can prove that it is if you want to, but yeah. Number C, so what's the smallest of these things? Well, we get out our engineer hats for some of this, and pretend that root 3 is about 1.5, so therefore this here, I mean it's 3 root 3, right, because it's root 3 times root 3 times root 3, the first root 3's make a 3, so it's 3 root 3, pretend this is 1.5, now it's actually bigger than that. Maybe you just know it's about 1.7. But if you just pretend that it's 1.5, then this is 4.5, which makes the original correct thing bigger than 4.5. Because this is bigger than 1.5, this is bigger than 4.5. So I'll just leave that there and say that's my engineer estimate. This one I don't have to estimate because I can just write 9 as 3 squared, then use the indice law that we used in the last question, then bring the 4 down, and 4 log 3 to 3 is just 4. Which is smaller than this, of course, because this is bigger than 4.5, so that's not the correct answer. So that's good. This one here, you should know sine of pi over 3 is root 3 over 2. So this is 3 lots of root 3 over 2 all squared. 3 squared is 9, root 3 squared is 3, so 9 times 3 is 27, 2 squared is 4, so this is 27 over 4, which is, I couldn't even be able to work it out. It's bigger than 4, right? It's bigger than 4, so sure. In fact, it's not even 7 point something, is it? It's 6.75. It doesn't matter. It doesn't matter, does it? It's not the smallest. Good. This one, same thing. This is 2 cubed in here. This is a log of a log, which is interesting. But anyway, this is 2 cubed. 3 times 5 is 15. Bring the 15 down to here, not all the way to the front. That's not how the log law works. Just down to here. And then you can say, well, this is 15 times this. I mean, this is just 1, I should have said straight away. But in any case, I said it was 15 times this, so it's log to base 2 of 15 plus log to base 2 of that. But that's just 1, which I eventually did work out. And then log to base 2 of 1 is 0. So you just get this. But this is less than 4, because log to base 2 of 16 is 4, because 2 to the power of 4 is 16. So this is less than 4, so that's the smallest one, because the other one is 4. Good. D, this is quite a nice question. You take this line here, and you gradually move it up the y-intercept here. So this c value is the thing that they're changing across these graphs here. And you gradually move, and the c value is the y-intercept, so you gradually move this line up here, and you're sweeping this black area of the square as you move the line upwards. Now, if you move the line upwards a little bit from here, you get to something like this, and that's some area that you've increased here. Right? You've increased this amount by just nudging c up a little bit. But when the area is bigger, like when the area is currently here and c is very close to 0, and you move c up a little bit, you suddenly sweep a much larger area for the same little nudge, because there's a greater distance across the diagonal of the square here than there was before. So for every little nudge of c that you give, the closer you are to the origin, the closer you are to the full length of the diagonal of the square, the more area you sweep out with that nudge, because you've got a larger distance here across the square. And so the area is going to increase at its largest rate when c is very close to 0. When c is far away from 0 and a little nudge just gives you a tiny little area here, as opposed to a much larger area here, or even bigger one here, then it's increasing much slower. So we're looking for a graph that has its greatest rate of increase when c is around 0. And the only graph that does that is A, so the answer just must immediately be A. Good. E. Really lovely question. I'm going to use this in all of my classes now whenever I teach chapter 4 of the textbook. So we've got a graph here. Now, first thing to note, it's a negative quintic, right? Because it's got 4 turns here, and it starts up there, ends up here. So we're looking for a negative quintic, and we're looking for it to have 2 repeated roots, so 2 roots that are squared, and 1 root that's singular. So okay, what does this achieve here? So this is I believe, a negative quintic, so that's good. It's got 2 repeated roots at 3 and minus 3, and 1 single root at 1, which meets all the criteria, except this single root at 1 would be between 3 and minus 3, not over here. So that one can't be right. This one has a repeated root at 0, which this clearly doesn't, so that's just not right, clearly. This has a repeated root at 2 and minus 2, and a repeated root at 6. Sorry, a single root at 6, which looks perfect, except it's a positive quintic when you multiply that out. So that can't be right. And this one here is, well, it must be right because it's the last one, but you can factorize this to be x minus 1, x plus 1, which you can then square to get x minus 1 squared, x plus 1 squared, so roots at minus 1 and 1, sorry, 1 and minus 1, and 3, and it meets all the criteria, so this one is definitely the answer, and it's the only one left, so that one's definitely the answer. Really lovely question. This one here, so think about what the cos graph looks like, and integrate between pi over 2 and minus pi over 2. Well, that's a positive area you've got there, right? So that's a positive number. This one here, the sine graph between pi and 2 pi, that's a negative integral, so that the integral of that is going to be a negative number. And this one here, now this is the most complicated one, 1 over cos of 3x. Now 1 over cos is fine unless cos is 0. This is called, by the way, sec. In case you don't know. That's fine as long as cos isn't pi over 2, or any of the other points where cos is 0, because then you're doing 1 divided by 0 and you get an asymptote. But the biggest, I mean, we're starting by substituting in 0, and cos of 0 is just 1, so 1 over 1 is just 1. And then the graph is going to go upwards, because cos is getting smaller, and when you divide by a small number, the thing will get bigger. So this graph is going to get bigger, and the last thing you input is cos 3 pi over 8, which is less than cos of pi over 2, or 3 pi over 8 is less than pi over 2. So you're stopping sort of about here, which means the graph will just go up and you'll sweep out a nice positive area with no asymptote, so that's just a positive number there. And so positive times negative times positive is negative, and the area, the answer to t is going to be negative. Good. Okay, so here we've got 2 simultaneous equations, and it says we want positive real solutions to these. And which values of k do that? Now let's just test k equals 2. I'm going to do this in an extremely lazy way, by the way. Just put k as 2 into here, and you actually end up with the same equation twice. Of course, this has positive solutions at 1 and 1. It also has solutions at 1/2 and 1.5, I think. Yeah, it does, right? Yeah, it does. But who cares? This definitely has positive solutions for k as 2. So this isn't the answer. This could be, and this could be. And to test, let's just use k as 0, because this one claims that it should work, right? This one claims that it should work for k as 0. Put in k as 0 and you get these 2 equations. This one gives you x as 2, but then you get y as minus 2 from that, which isn't allowed because we need to be positive. So this doesn't have solutions for k as 0, which means this one is wrong, and also means this one is wrong, because this one says that it should have them for anything, which means the answer must be C, just by very lazy deduction. H is a really interesting question. I've never considered what this graph looks like, but essentially this question asks me, unless you want to do some crazy substitution and actually do the integral directly, this question essentially asks you, what does this graph look like? So of course we start off with the sine graph, and I've plotted this very weirdly, look. I haven't used the normal pi here and pi over 2 here. I've just done it in like raw numbers. So this is 3.14 there, of course, and this is like 1.6 roughly. And there's a reason I've done that. That's just y equals sine t. Now let's consider what sine of t looks like. Notice how this graph is sine of t, which is going to be the inputs to your new sine, are always between 1 and minus 1, which is interesting. And so the inputs are going to be between here and here, right, on the next graph. Let me just show you what I mean. So if I'm trying to sketch sine of t, if I use t as 0, sine of t is 0, and sine of 0 is still 0. So it goes through 0, 0. Then I'm just going to use t as a half, right? I'm just going to input t as a half. Now, sine of a half, I can see here, is roughly a half-ish. And so this is, sine of a half is roughly a half. Again, I'm full engineer mode for the third time this video. Sine of a half is roughly a half. And then sine of a half, if I go back to this, is, well, that's just a half again. So we end up with something that looks a bit like this. And then I can put input 1. So sine of 1 is like 0.8, it looks like. And then we do sine of 0.8, which is like 0.7 maybe. So we end up with that point. And now I can input sine of, well, I know it's pi over 2, but I could just call it 1.5, just fully leaning into the engineer mode. So if I put t as 1.5, I get 1 out. Sine of pi over 2 is 1, right? And then I do sine of 1, and sine of 1 is about 0.8, as I just said. So it peaks at 0.8. Notice that's the peak, because that's the biggest thing I'm going to input into the sine. And then if we go with 2 gives us, or t is 2 gives us sine of 2 is like 0.9, and then 0.9, sine of 0.9 is like 0.7 or 0.8, as we said. And so it goes back down, and then it goes back down until you get down to pi, and at pi, sine of pi is 0, and then sine of 0 is 0. So we end up with basically exactly the same curve as we have here. This is not looking very symmetrical, but whatever. We end up with basically the same curve, except it peaks a bit lower. That's all it is. And then we keep going, and we say, okay, well, let's input 4. When t is 4, sine of 4 gives us about minus 0.8. So then we input sine of minus 0.8. Sine of minus 0.8 is like minus 0.7. Right? So we end up going down a little bit. And we go further down, right? When we use 3 pi over 2, we get minus 1. And then sine of minus 1 is like minus 0.8. Or whatever it is. So we end up curving down, and then exactly the same thing happens. As we go back up again and use maybe 5.5, we get minus a half, and then we input minus a half, and we get roughly minus a half, and we come back up again. And then when we use 2 pi, sine of 2 pi is 0, and then sine of 0 is 0, and we end up with basically a sine curve, except it just has its peaks at like roughly 0.8, we decided. And that's really interesting because it allows us to answer this question, because from what bounds can you integrate this function and get 0 if you start at 0? Well, to answer an integral with 0, you need to have lots of cancelling out happen, right? So what value of x can I choose to integrate up to have all of this area cancel out? Well, the obvious choice would be x is 2 pi, right? If I integrate this between 0 and 2 pi, because it's supposed to be perfectly symmetrical, just like the original sine graph, these areas will cancel, and I'll just end up with 0. And I think that's the only value I can pick between 0 and 2 pi. That's the only value that will actually cancel out everything properly if I'm starting at 0. So I think there's only one solution to this, my picture says. Excellent, so just a couple more questions to go. We've got a triangle labelled XYZ, it's equilateral, and a circle going around it. Good. Circle has circumference 10, which means 10 is 2 pi r, which means r is 5 over pi. So all of these distances are 5 over pi. Now, I think I can work out the area of this triangle here. So P and A be the areas, perimeter and area. The area of this triangle is going to be 5 over pi times 5 over pi times a half times sine of 120, just using half times a b sine c, times by 3. Now this is 120, of course, because there's 360 here, divided by 3. So the area is 3 lots of half times 5 over pi times 5 over pi times sine 20. And that's the 3 triangles. Sine of 120 is root 3 over 2. You can look at the sine graph that we had up just before if you want to confirm that. But essentially you end up with this, which simplifies to this. And that's my area, I think. Now what about the perimeter? Well, if I call this length L, I can use cosine rule, right? I can say L squared is equal to 5 over pi squared plus 5 over pi all squared minus 2 times this times cos of 120. And now again, cos of 120, this is 5 over pi all squared, of course. This is 5 over pi times 5 over pi. Cos of 120 is, again, get out the cos graph if you need to, but it's minus a half. So this turns into a half and changes that to a plus. And this half cancels with this 2, and you just end up with 3 lots of 25 over pi squared added up, which is 75 over pi squared. And that's L squared. So if we root that, this is 25 times 3, so the root of that is 5 root 3. This is, of course, just pi, and we end up with this. And now the perimeter is just 3 lots of L, right? So the perimeter is 3 lots of that, which is 15 root 3 over pi. So I have my perimeter, and I have my area. which is good. And now it's asking me which of these things is true. Now this one doesn't look true because when I square this I'll end up with a pi squared on the bottom, so that doesn't really seem very true. I could assess this, but I noticed that both of the other two have something to do with p over a and a over p. So let's just work out a over p first and see, and like if a over p is equal to 3 pi over 10, then I can just flip it over and it's this one. So let's just work out a over p and just hope it's one of these two things here, or at least this one upside down. Well, a over p is this divided by this, by the way, if it's neither of those things, I know that this is correct immediately because I'm pretty sure this is wrong. These pi's cancel, or at least one of these does with this. These root 3's cancel. This 75 divided by 15, the 4 chunks down to the bottom. The 75 over 15 is 5, so this and the pi also goes to the bottom. This is equal to 5 over 4 pi, which is indeed this answer. And we have the answer of A. Good. Last question. I'm going to do this in a little bit of a weird way. There's probably a correct way of doing this. But firstly, I just need to argue that so we've got an area here in this circle, and it's asking us what the largest possible area of this shaded region is. Now we know from circle theorems that you can put this point P anywhere on this arc between Q and R, and the angle theta is the same. That's just the circle theorem that we know at GCSE. And I'm going to argue that the place to put it such that you get the biggest area in here is bang in the middle of Q and R. And the way that I'm going to argue that is by splitting the area into 2 bits. This sector obviously doesn't change when you move this point around this arc, because it's just staying motionless there. It's only the area of the triangle that changes. But the area of the triangle, wherever you put these two lines, always has the same base, and its height perpendicular to it is at its largest when you go straight out to the end of the circle here. Right? So for example, this triangle here has a bigger area than this triangle here because you're using the same half times base, and the perpendicular height is taller when you're right out in between Q and R. And so the biggest area you can get is when you put this angle theta in the middle of Q and R. So that's the first thing I'm going to say. The second thing I'm going to say, and I'm going to cheat essentially, is I'm just going to put Q and R in the most convenient place. I'm going to put them right in the middle, making a diameter of the circle. And this gives me 2 really helpful facts. It gives me that this angle here, of course by circle theorems, is 90 degrees, or pi over 2. And it also gives me that this length here is 2 lots of the radius, because it's the diameter, which is 2. And now I can just do some Pythagoras. Root 2 squared plus root 2 squared is 2 squared. So these lengths are root 2, and I can work out this area because this is just half of a circle, radius 1, so it's pi times 1 squared over 2, and this here is just half times root 2, and that's it, because it's just a triangle, half times base times height. This of course just makes 1, and this of course just makes pi over 2. So the area, when you use Q and R being the diameter, is the area when the angle is pi, when you use Q and R as the diameter, which forces the theta to be pi over 2, the area is 1 plus pi over 2. So all I have to do now is verify which of these formulas in terms of theta will give me this result with this theta. And if they don't give me this result, this can't be the correct general formula. So I found one time in which theta of this angle gives me this area. If these formulas don't work for that theta, and give me this area, then they can't work for any other value either, can they? So I just need to verify which of these formulas work properly. So let's try first. Let's put theta as pi over 2 into here. Cos of pi over 2 divided by 2 is pi over 4. Cos of pi over 4 is 1 over root 2. So this has a root 2 in it, so that doesn't work. This here just gives me pi over 2 plus sine of pi over 2. Sine of pi over 2 is 1, so that one actually works, which is good. Now, I can't underline it straight away because it might be that something else works for this special case. So pi over 2 into 1 minus cos pi over 2, this is 0, so this gives me pi over 2, which is wrong. And then this, of course, just gives me pi over 2 as well, which is also wrong. So this one is the only one that works for this case, and thus is the only one that could possibly be the actual formula for general thetas, and so therefore is the answer. Thank you for watching, and I'll see you next time.